Hello and welcome to KAUST Live. Well, we're coming to you from the Clean Combustion Research Center's Research Conference on Extreme Combustion. Here to talk to us today about that and their research are Professor Robert Dibble and Mara de Joannon. Thank you both for joining us.
Thank you.
Thank you.
Yeah. So to get us started, tell us a little bit about what both of you are talking about and doing at the conference. Maybe we can start with you, Mara.
Okay. My talk was focused on an advanced combustion technologies that now is spreading in several fields of technology that is named mild combustion. Other people name it flameless combustion, noiseless combustion, because it is very particular combustion process because search for efficient condition, working condition in, let me say, in extreme condition. And it is a very clean process, very really flexible, and in some way it answers to the main point tip of, energy request, energy production system request.
I see.
And with respect to the standard combustion process, it works in a very diluted condition and preheated condition, and you can reach a very characteristic situation where you can look inside the combustion chamber, but you cannot see a flame. This is why often it is also indicated as flameless combustion. So it is a totally different with respect to the standard combustion process, and it is clearly stated that our research on that we have to change the paradigm with which we have to look at the combustion process in order to address the new request of energy production with the combustion-based system.
So where, give us a sense for where this might be applied. Is this on the infrastructure level to generate electricity, or is this on the personal level with cars and that sort of
but this process, one of these a good point that it could be used from the microscale to macroscale. So both for distributed energy production, it is very important, especially if you look at the concept of the spreading concept of smart grid, and so to be really integrated in renewable energy grid, and also on big system like there is people that is exploring that for gas turbine application, for several on macro scale. So.
I see. Very good.
And the other point you talk about engines, cars, and so on. When you look at the new advanced technologies, they are altogether, if sometimes they speak different language, but altogether towards the same working condition in the combustion chamber. So we generally, the mild combustion refers to a combustion process where we have low maximum temperature with respect to the standard combustion process. These lead to a reduction of pollutants. But the same condition in some way are reached in new advanced combustion technology for engine, let me say HCCI or IRC-CNR engines.
I see. Okay. Very good. Dr. Dibble, what are you doing and speaking about at the conference this week?
It turns out most of the audience there are postdocs and graduate students. We have maybe 20 speakers that came from various parts of the world. But still, the bulk of the audience are graduate students and postdocs at KAUST. And I recall that I once was a postdoc, and back in 1976, I was lucky to have a one-year National Science Foundation postdoc at Imperial College London. And I had studied chemical engineering with a particular emphasis of using lasers to make new chemicals. Now, the fact that there are no chemicals that are made with lasers today it shows that I failed on that. Nonetheless, I did win this postdoc to study about energy in 1976. And of course, I remember many good things about that year, but amazingly, at Imperial College, no one spoke of CO2 as a problem, not in 365 days of being in a combustion program. And number two, I was assured that by the year 2000, all that would be left would be coal. The petroleum would be gone in 25 years. And so, you know, neither of those are correct. Therefore, I was quite confident that what I said today was also wrong. Okay, and so that is the basis of what I talked about a lot, was trying to say, where are we and what's the future? And my talk was different than most in that I'm really looking at the CO2 problem, and that the combustion people are the problem, and that if that's true, then the combustion people have to solve the problem. And what science are we doing even at this meeting that helps solve this problem? And it's an overarching problem, and it won't go away conveniently. And so the good news is, in combustion world, this now opens the door for things that you thought of doing 20 and 30 years ago, but everyone said, nah, too expensive. We don't want to do that, you know, waste of time. But now we have to entertain a lot of ideas, including what she has in terms of, I call it, what we used to call it, oxy-fuel combustion. No, anyway, she's we call it mild combustion now. What do we used to call it?
Flameless?
Yeah, flameless, yeah, FLOX, flameless oxidation, FLOX, okay. So it's changed names in 20 years.
Right.
But 20 years ago, it was a curiosity. And now I look at it as a very serious contender as to what we must be doing. Things like that. And so
you talked a little bit about, and get to this maybe, how much, like to what degree does a flameless engine actually reduce pollutants? How is that part of a solution? Maybe you both can sort of address that. So the flameless engine, I think you had said, creates less pollutants. So how does it actually create less pollutants?
Well, here's how I know that when I watched her talk, I showed people that we have a very serious need to do combustion at 300 atmospheres. And typically, if things like this is only encountered in rocket motors for a short period of time, maybe 6 minutes or something like that. And when we go to 300 bar, the combustion that we now know, is increasingly people are knowing and they're suspicious that our paradigms aren't going to work. And certain chemical reactions that we rely upon are simply not going to work for us, and other things must happen. What she's working on is kind of in that area that I suspect that what she's doing can be elevated to 300 bar and still work. And she had no idea that that's where I'm thinking and that's where I'm coming from. So I look at the whole conference and I exhorted everybody in the room. They said, in my talk, I want you to think, how are you going to help me? And how does the many vast subjects that we have that are relevant to combustion, and now how do they help the CO2 problem?
At what bar does, I will say, general combustion happen at in a combustion engine in a car, for instance? What's the pressure that's happening at?
Car engines are typically around 100 bar.
Okay.
And they start combustion at maybe 50 bar. So just as combustion starts going, then finally the pressure rapidly increases up to like 100. In diesel combustion, you might be starting at 150 bar and then going over 200. This number is steadily increasing. So 20 years ago, I had to promise that I would not exceed 200 bar in my diesel engine before they gave it to me. And but nowadays you have to promise not to exceed 300 bar. Okay, so it's steadily increasing.
I see. Mara, do you want to add to that?
You asked before how we reach the clean combustion
Yes.
condition, because you want to increase the pressure, we want to reduce the temperature. Maybe the two stuff are very well connected in
Could
some
be.
way. Yeah, yes.
I think can be.
Yes, I hope. And why? Because reducing temperature, you avoid formation of main pollutants because of the kinetic. The kinetic is very. The kinetic rate is very low at temperature characteristics of a mild combustion. For sure, the one of nitrous oxide formation and also soot formation, so nanoparticle formation, and this is why we have a process that does not produce pollutants.
I see. Okay. Interesting. So having that lowered temperature, having that increased pressure somehow helps to reduce or did you say eliminate the nitrous oxide?
Yes, at ambient pressure, yes. We can reach 1 digit NOx and the absence of nanoparticle and soot formation. So it's a very good advance. But as told about maybe 20 years ago when this concept started, no one wanted to give money for that because it was not sustained by any real facility. Now the research is going on and we proved that these conditions are very useful and the concept is very strong to be applied on large scale.
Do you test this in actual combustion engines? Do you do modeling? Do you do some mix?
I am focused on experimental work, and with my work I tested it on lab scale, very elementary reactor. But now we have a burner. Let me say always a lab scale burner that but work in a range of power that can be directly used in a practical application, but at atmospheric pressure. That is very nice for, as I told you, for distributed energy production, where that is very important for the smart grid concept of in the city.
I see. Dr. Dibble, are you combining these higher pressures with certain fuels, green fuels that you're making? Talk a little bit about biomass and producing green fuels, ethanol, this sort of thing.
Make sure I get to that question. I want to comment on what she said about, and you asked about numerical modeling and experiments. And I preach to graduate students and postdocs that they have to do both, that their ship can't list to all experiments or can't list to all numerical modeling. I want a balanced ship, and that's expecting a lot. It might be a little bit this way, it might be a little bit that way. In my career, I balanced the ship by working closely with numerical modelers. My dearest friend in Berkeley is Professor Chen. I hope he's watching. And he and I have been a great team for years in balancing numerical modeling and the experiments. And I think it was today somebody put up a one line that just said, we do modeling not to agree with the experiments, but merely to sharpen the next set of questions. And many people, senior people in the audience nodded their head. They said that's correct. So the modeling is as the model gets better, then the questions get tougher. And when the questions get tougher, the experiments have to get a little bit more careful. So we always smile and say the easy experiments we did 10 years ago, now we really have to work. And the same with the modeling. The modeling people look back and say, gee, we had it easy 10 years ago, and now it's hard. But of course, you smile and you say 10 years from now, they will say exactly the same thing. Okay, so it's I think that's the steady march of science. Now, to your question about green fuels, yeah, my overall one more comment. There's still talk about nitric oxide, and it was a pollutant that was completely uncontrolled, and we started to control it as late as 1975. So in my professional lifetime, I could see nitric oxide regulation come in. The first automotive catalyst, three-way catalyst, was 1976. Pollution measures on power plants and so on come on in a similar period of time. So people like me can thank nitric oxide and sulfur dioxide. It made our life possible. Okay, we made a living on trying to minimize the production of this minor pollutant, and excuse me, it's there in parts per million. You know, maybe 700 parts per million, 500 parts per million. She's able to get to 10 parts per million, even lower, which is remarkable, and things we didn't dream of 30 years ago. But I tell this generation of scientists, the postdocs and the grad students, that CO2 is what's going to bring home their food and put beer in the refrigerator, okay? Important. And so CO2, one mitigation of CO2 is where you went to was biofuels. That is, if we grow plants, and the plants grow by taking CO2 out of the atmosphere, then we call that CO2 neutral. We took some CO2 out and we put the same amount back in. So, you know, that's considered okay. And, you know, my degrees are all in chemical engineering, and I found myself in a faculty of mechanical engineering. So I'm quite excited that I span both, you know, chemical synthesis, chemistry, organic chemistry, one of my favorite classes. And then I try to understand how do machines work, what fuels do they need, how does fuel viscosity, vapor pressure get involved into the machine. So I felt pretty good that I could expand both spaces. I have spent a long time, like others, on biofuels, and they've been resistant to solving our problem. It comes down to we're not able to produce enough biofuels quick enough. There is some discussion that as we take the case of biodiesel, well, it's made from vegetable oil, and more often than not, that vegetable oil is also a food. You know, could be olive oil, could be any sunflower seed oil. Just lots of oils, and so there, people raise an eyebrow and say, it looks like you're competing between food and fuel. I smile, and I have a picture from 1800 of Piccadilly Circus in London, and you see all the vehicles are pulled by horses, and the little note says all vehicles had 1 horsepower. Okay, and the little note that said 1/3 of all agriculture was used to feed the horses. So I said in an earlier time, 1/3 of all of our agriculture business was to feed our machines that moved us around. Right. So nowadays we are talking like that would be evil to do that, but I said we already did that. Okay, so
what's the future of that? Where does that end up going?
What's happening? Thanks for asking that, Nick. Because what's happening, and it was out of my control, but I started to realize this is what's happening. Is we call it electric fuels, and the growth of photovoltaics and wind power were not predicted. They're doing much better than we anticipated even 10 years ago. And so we're producing enough low-cost electricity that it's now conceivable to use that electricity to make fuels from carbon dioxide. So just like a plant that pulls the CO2 out of the air, we have the same opportunity to pull the CO2 out of the air and then take it into a chemical reactor and bring in electricity, which could be as simple as electrolysis of water to make hydrogen and oxygen, but bring all that together and synthesize and come out with fuel such as methanol, such as ethanol, such as hydrogen itself. And we would call all this e-fuels. And I have to suck air through my teeth and say, amazing. This looks to me like it's a horse that's going to win ahead of biofuels.
Because it's that stored potential energy,
yes.
Essentially. You can now, it's portable.
And the fuel that you produce is the word frangible means it's drop in. It means you can kind of continue business as usual, namely driving your car, but now the fuel will be entirely renewable and therefore CO2 neutral. And this is good.
Right. You also work on the conversion of waste heat into power. Talk a little bit about your work on that. Does that involve combustion engines, and then you conserve all that power that's wasted in heat? How does that work exactly?
There's several facets to that, but historically, go to a place like where we're at in Saudi Arabia, fuel was abundant and low cost, and therefore you would not spend a lot of money on the engine to convert the fuel. That is, if the engine was affordable and it was 20% efficient, you'd say that's fine because the fuel is almost free. So over the last 30 years, historically, the oil countries around the Arabian Gulf, they used many gas turbines. Now, these gas turbines, when it's 20% efficient, that means it's 80% waste heat. And so that means the exhaust of these turbines is blistering hot. And one person laughed and he says, "We are trying to heat the desert." Okay? And so that's waste heat. And if you have an apparatus like, we talked about organic Rankine cycles, where you can just simply plug in behind these things and just have the heat do something to a working fluid, you are generating more power. So the efficiency of the whole operation is going up, and you're not burning any more fuel, so your CO2 signature is zero. So it's a good thing to do. And
what percentage can you siphon off of that 80%, do you think?
Certainly, you can. I'll give you an example. If you buy a big, say, 250 megawatt power turbine from GE or Siemens or I think those are the main providers, there's enough waste heat on that 42% turbine that you put on a downstream Rankine cycle that runs water, so it's a steam cycle, and you will gain another 20%. So you had 42, now you gain 20 more, so the total package is 62% efficiency. And that's hard to beat. That's very hard to beat. Now, that's a lot of hardware, and remember, you got 300 megawatts of gas turbine, 200 megawatts of steam equipment, but you can see it's worth it. I mean, and again, the steam cycle is picking up merely waste heat from the gas turbine cycle.
Conceivably, could desalination plants be run off this type of thing as well?
Certainly. Yeah. I mean, that's. They can run directly off the electricity generated, or probably better if you take just the waste heat and directly use that to run the desal plant.
Very interesting. Mara, you're part of a European group called Smart Cats, which even the logo has a cat in, which I thought was quite cute. Talk a little bit about what that is and your work.
Yes, this fit very well with the concept of the energy carrier that's introduced Bob, because this is a networking project in the framework of cooperation in science and technology that is under the umbrella of Horizon 2020. And it is I coordinate this network of 29 European countries that work on the spreading of energy carrier on a large scale and in an efficient way. What does it mean? That the people involved in this project that are generally named cost action because they have a particular name. work on the fundamental knowledge of for the use on energy carriers. That means on kinetics, on kinetics of conversion, of pollutant formation, or destruction, or on diagnostics, and try to use this knowledge to develop or to help developing of advanced combustion technology for using them. And to what we refer when we talk about energy carrier. In that project we are used to talk of smart energy carrier, but they cover a wide palette of carrier that go from the fossil fuel to biofuel, to the fuel that are used to storage energy in the in the renewable energy grid in case of excess of energy. So now we are trying, for example, this is also was one part of my talk was focused on that, on the trying to use ammonia, that is one of the potential energy carrier for the energy storage, wind and solar energy storage. So the people involved in this action share the idea and sharing people, because this is an excellent project to support young people to visit other laboratories, other countries, and to organize excellent meeting to discuss and to project to discuss for on the future of the research in this field.
Yeah, to drive around Italy is to see quite a lot of solar power and photovoltaic panels and wind turbines as well. How much of a mix is that in power generation in Italy in general?
You know that in Italy, yes, there is a lot of solar power generation. Generally, during the summer, we can just use solar and wind generation.
Wow.
But I would underline that our field of research goes along with the fusion of this renewable energy. This is because of the intermittency of such source, and this is the first point. The other point is that in case of failure on some part of the grid, the only backup can be assured by means of a combustion system, because their characteristics are unique, and the only one that can support the energy grid based on renewable to support a possible failure. The other point is the storage of energy, as I told you before, because the chemical storage maybe now is the only really possible now, because the batteries or other systems are still limited in time and in capacity. So the backup that could be done with the chemical storage and use the chemical carrier in a combustion system is the most efficient available in this moment.
Mm-hmm. Are you working to try and couple some of these renewable energies, as Dr. Dibble said, to make some of these e-fuels in a way to create green fuels with solar or wind energy?
Not because we are focused on the use of the carrier.
I see.
There are very, wide, several fields of research that you can explore to make this system apply. But there is already exists the technology to have hydrogen and from hydrogen ammonia to be used in. So this is not the critical point. The critical point is their efficient use to produce energy.
I see. Now, as a background, you said actually you're in chemical engineering is where you came from, so you both did, but now you're a professor of mechanical engineering. So talk a little bit about how that frames the way that you do your research, if at all. I'm just curious to know how it directs the way that you do your work.
Okay.
Mara, please go.
Thank you. My background, of course, helped me, drove me toward the study from the process point of view, and that is so that understand how to evolve in its intrinsic nature. I don't know if it is clear. So to look inside the process and sometime to put it in to connect it to a unit, but we are more focused on what happened inside. So the chemical evolution, but also the fluid dynamic, the coupling of fluid dynamic and chemistry. And now with the new advanced technology, the coupling of both of them is more difficult with respect to other field of research. But I think that this is the main characteristic of chemical engineering. So to look at the system studying the process.
Dr. Dibble?
Well, if you're a mechanical engineer and somebody says, can you burn ammonia? That's a question that they might think, gee, do you want me to burn in a spark engine? Do you want me to burn in a diesel engine, gas turbine? Well, sort of what are you thinking? What's the need? And you need to do that. Now, if you have a chemical engineering background, you can quickly also ask yourself, where does ammonia come from, and why are they asking this question, and is that reasonable that ammonia could be a fuel? And if it is, then you go back to the mechanical engineering questions and you say, this is a more serious question than just an academic question. People are very serious that ammonia is simply a carbon-free fuel. So combustion of ammonia doesn't produce CO2. This is interesting. Furthermore, the ammonia is generated from hydrogen and nitrogen, of which the air is full of the nitrogen. So the hydrogen we would generate from water splitting, and that again would come from the renewable excess, we say, but renewable electricity from the windmills, from the photovoltaics. So the path to a carbon-free future, we have to take that serious. Can it be ammonia? And she surprised me today that in her reactor she was burning methane, I believe, and oxygen and propane. I saw propane. And then she said, we'll try ammonia. And I leaned forward in my chair. I said, this will be interesting. And she showed that she could burn ammonia in some very clever ways and produce no nitric oxide, no pollution, complete combustion of ammonia. So to me, that's a high watermark. I hadn't seen anything so effective as what I saw today.
And again, was that for large-scale infrastructure, or was this simply modeling of things that could be done, or was it thinking about personal use vehicles? Give us a sense for that.
Our partner is up to work so far up to 10 kilowatts, so for a domestic application. But this is just the first step, because first of all it could be we can increase the power with the numbering of the use more than one burner together, but it is always for a small scale. But I know about other projects, not in Europe, but in Japan, that is focused on a large-scale application of ammonia combustion.
Yeah. What's the feedstock for that? Where do you get these abundant stocks of ammonia to burn in a potential
but
engine?
You obtain it from, there are several chemical processes that can allow you to have ammonia, but the ammonia maybe is one of the most used product in the world, probably. So there is all the technology to have ammonia. The point is to have ammonia from as you underlined before, from solar and wind energy. But then the step is to produce hydrogen, and from hydrogen to have ammonia. So the way is there.
Fascinating. Fascinating. Anything you want to add to that?
Well, as Mara says,
Yeah.
you can generate hydrogen from the electricity that you would get from wind power and from the sun. That electricity, you can split water, and we've known how to do that. And we should work on improving that, although people said we've been working on that a long time. And so nonetheless, we can split water electrolysis. You have hydrogen. Hydrogen, then you can combine with ammonia over a smart catalyst, and that would make you ammonia. Another route is people take the hydrogen and pull CO2 out of the air, combine that, and you can make methane. The car company Audi has one program where they are making methane with excess electric power in Germany. They push that methane into the pipeline. Then they sell natural gas automobiles. And if you buy this automobile, they give you a credit card that you swipe at a natural gas station and you get charged nothing. You can fill up your car forever. And that natural gas has already been paid for by Audi. And if you do the numbers, Audi put in green natural gas. So they're telling the drivers that you are driving on green natural gas. Now we both know that, look, they put green natural gas into the pipeline, but it's full of also fossil natural gas, and when somebody draws out of it, they probably got fossil natural gas. But to the people who keep the books, green gas went in, you took the green gas back out, and so you were driving your car on green gas. So many customers have signed up to this. This is a very good marketing strategy for Audi. This morning we had a speaker who was showing how an airplane engine burning natural gas, if properly managed, could reduce its CO2 footprint by 50%. Now to the aircraft people, this is big. They like to see that. But then I smiled and said, if that same aircraft company would follow Audi's lead, and that they merely just generated green natural gas and put it in a pipeline, then you could argue that airplane is entirely CO2 neutral. Just did not add any CO2 on the long 12-hour trip.
Right.
So it's a very exciting times in combustion, and I think combustion has to embrace not just the burning of the fuel, but where did it come from? How did we get it? I mean, it's exciting because just like there's smart catalysts, just like there's her kind of flameless oxidation. It's exciting because you get to put your hand in all these things, and I call it wide bandwidth. You have to have wide bandwidth. Okay.
Right. Well, Dr. Dibble, Dr. Joannon, thank you so much for joining us. Hope you
pleasure.
enjoy the rest of the conference and your stay here at KAUST. And thank you to all of you for joining us. Please come back soon. Check the Facebook page. We'll have more of these as the OSR conferences continue. Thank you and good afternoon.